right? So this promotes us to really look into how do we compute all of these gradients, right? So for essentially, we have looked at unconstrained optimization requires the gradient of J. All right, and the constraint at least some approximation of the second derivative, also called the Hessian. Usually, the Hessian approximation is not that important, and the gradient is a lot more important than how well you approximate Hessian. And the constraint optimization requires all that is required for unconstrained optimization. So the first order derivative, the second order derivative, plus the gradient of the constraints. Okay, so the question now becomes, how do we compute this? And we're going to actually focus on the gradients of the objective function and the constraints. The Hessian, we can discuss that. I mean, there are plenty of ways to approximate that if you use quasi-Newton or if you follow steepest descent. Okay, and also the method that computes the gradient can also be generalized to computing that of the Hessian. So in numerical calculation, it is quite rare that we're going to have analytical formulas to calculate these derivatives. So we're going to focus on numerical methods of computing these derivatives. The most obvious way of computing these derivatives are using finite difference, right? So we want to compute our derivative of J at S0. We can obviously just approximate it with finite difference. So finite difference requires us to make a small perturbation to J, right? So plus, for example, an epsilon times the vector 1, 0, etc. So we are only perturbing the first design variable by epsilon minus J S0 divided by epsilon. So that's going to be the first component of the derivative. Okay, and the second component of the derivative is going to be J of S0 plus a same epsilon but perturbing the second dimension minus J of S0. So divided by epsilon, etc. Right, so essentially, if J involves performing a simulation, this finite difference approximation essentially perturbs one of these design parameters at a time and performs another simulation with the perturbed parameter and compares the output of the perturbed simulation with the output of the unperturbed simulation to figure out what the gradient in a particular direction is. So in this method, the computation cost or the number of simulations, if J involves a simulation, is equal to D plus 1 if the for a D-dimensional design parameter S, right? So this is actually one of the pretty common ways to compute the derivative. It is pretty computationally feasible if D is small. if you're designing an airfoil, for example, you have 10 or 20 design variables. It's pretty common to use finite difference to compute such derivatives, not only for the objective function, but also for the constraints. It becomes more problematic once you start designing a three-dimensional surface, like a airplane wing. When you start getting to the regime of hundreds of design variables, the computation cost starts to get pretty out of hand pretty easily. And the more problematic case is in some applications when you want to figure out, oh, what's the best mesh for me to simulate a particular problem, right? Where should I refine the mesh? And sensitivities like that is going to be very difficult to compute using finite difference, because the possible locations you can refine your mesh is pretty much infinite. And this is something we're going to be talking about in our next lecture, that is using the idea of adjoint, or it's also called a backpropagation in some of the more recent literature, to compute gradients like that, not only for optimization, but for other applications like machine learning. So I will see you on Wednesday. If you have any questions, feel free to stay and ask.